Hello everyone, I am Darshan A, Assistant Professor of Mathematics. In the previous sessions, we have learnt about limits and continuity. In this session, I am going to introduce you differentiability. First, I am going to define what is derivative at a point. Then, I am going to define what is left-hand derivative and what is right-hand derivative. When we say that a function is differentiable at a point, when it is not differentiable at a point, and then I will try to give an intuitive idea of derivative at a point, the left hand derivative and right hand derivative. And finally, we shall see some properties of differentiability. Let's get it. Let us start with the formal definition of derivative at a point. Let f of x be a function defined on a domain capital D. Let C be a point in the domain. Then if limit of f of x minus f of c divided by x minus c as x tends to c exists, then it is known as derivative at a point x equal to c and is denoted by f dash of c. If this limit exists, we say that f of x is differentiable at x equal to c. So when we find out a limit, we can find the limit approaching c from the left hand side or from the right hand side. That is, we can find the left hand limit or right hand limit. If this limit exists, left hand limit exists and right hand limit exists. The corresponding left hand limit and right hand limit for this limit is known as left hand derivative and right hand derivative at the point x equal to c. So the left hand derivative of f of x at x equal to c is the limit of f of x minus f of c divided by x minus c as x tends to c from the left hand side, and it is denoted by L of f dash of c or LHT. To find out this limit, we substitute x equal to c minus h and take limit as h tends to 0. So I get here limit of f of c minus h minus f of c divided by c minus h minus c as h tends to 0, or limit of f of c minus h minus f of c divided by minus h as h tends to 0. Similarly, the right hand derivative is the limit of f of x minus f of c divided by x minus c as x tends to c from the right hand side. It is denoted by r of f dash of c or RST. To find out this limit, we substitute x equal to c plus h. So this will be equal to limit of f of c plus h minus f of c divided by h as h tends to 0. Suppose if f of x is differentiable at x equal to c, then f dash of c exists. So clearly LHT and RST exist and they are equal. So L of f dash of c and R of f dash of c exists and they are equal. The common value is f dash of c. Suppose if L of f dash of c or R of f dash of c does not exist, or both of them exist and they are not equal, then we say that f of x is not differentiable at x equal to c. If either L of f dash of c or R of f dash of c does not exist, or exists but L of f dash of c not equal to R of f dash of c, then clearly f dash of c does not exist. In other words, f of x is not differentiable at x equal to c. Then f dash of c does not exist. Okay. Now let me try to give the geometrical intuition of derivative at a point. By the definition, the derivative of a function f of x at a point c is denoted by f dash of c is the limit of f of x minus f of c divided by x minus c as x tends to c. If you observe this value, Geometrically, this is the slope of the line joining the points x comma f of x and c comma f of c. Let us see this by considering several examples. First, I consider this example f of x. Let this point be c. So this point is c comma f of c. First, let me consider a point x comma f of x on the left hand side of c. Let this be x comma f of x. So the line joining these 2 points is this line. Okay. Clearly, this line has a positive slope. When I start moving towards C, suppose if this moves here, I get this line. So the slope started decreasing. When I approach here, the slope becomes 0. Similarly, when I approach from the right hand side, first I consider a point on the right hand side x comma f of x. This line has a negative slope. When I start approaching C from the right hand side, this point start moving towards this point. The slope of the corresponding line started increasing, and finally when it approaches this point, the slope is equal to 0. In other words, left hand derivative at this point is equal to 0 and right hand derivative at this point is equal to 0. Since left hand derivative and right hand derivative are equal, derivative exists at x equal to c and is equal to 0. Now consider one more example. Consider a graph like this, f of x. Let this point be C. First, let me consider a point on the left hand side. When approaching C from the left hand side, first I consider this point x comma f of x. The line joining these 2 points x comma f of x and c comma f of c is a straight line parallel to the x-axis, so the slope is equal to 0. Even if I move further, I get the same line, so the slope is again equal to 0. In other words, left hand derivative at c is equal to 0. But when I move from the right hand side, first I consider this point x comma f of x. So the line joining these 2 points is this line. This has a negative slope. Clearly it is not equal to 0. Even when I move further, again I get a line which has a negative slope, even less than the slope of this line. So when I approach C, the slope of this line will be minus infinity. In other words, right hand derivative does not exist for this function at this point. Since right hand derivative does not exist, derivative does not exist at x equal to c. Therefore, f dash of c does not exist. If I observe here, this is a continuous function, this is a point of continuity. I got here f is differentiable at this point. This is a discontinuous function and c is a point of discontinuity. I got f of x is not differentiable at this point. Now let me consider one more example. Now the function is continuous at c. Now let us find out the derivative at this point. Again I do the same thing. I consider a point on the left hand side. I get this line. the slope of this line is a negative value. If I consider a point on the right hand side, the slope of this line is a positive value. If I consider any point on the left hand side, the slope of the line joining these 2 points has a negative slope. If I consider any point on the right hand side, the slope of the lines joining these 2 points has a positive slope. So clearly the left hand derivative and right hand derivative are not equal. So f dash of c does not exist. The other way of convincing this statement is, at this point I can draw infinitely many tangents. Since the tangent is not unique, f dash of c does not exist. Now let me consider a property of differentiable function. If a function f of x is differentiable at x equal to c, then it is continuous at x equal to c. To prove this, given that f of x is differentiable at x equal to c, so by the definition f dash of c exists. This implies f dash of c, which is equal to limit of f of x minus f of c divided by x minus c as x tends to c exists. Now consider limit of f of x minus f of c as x tends to c. Now I multiply and divide x minus c to this term. So this will be equal to limit of f of x minus f of c divided by x minus c into x minus c as x tends to c. If I consider this as a product of 2 functions, first function and second function, by the algebra of limits, this will be equal to limit of f of x minus f of c divided by x minus c as x tends to c into limit of x minus c as x tends to c. Since this is equal to f dash of c and is finite, this is equal to f dash of c into, as x tends to c, this will be c minus c, which is equal to 0. So I get f dash of c into 0 is equal to 0. I have a limit of f of x minus f of c as x tends to c is equal to 0. If I take minus f of c to the right hand side, I get here limit of f of x as x tends to c is equal to f of c. And therefore, f of x is continuous at x equal to c. And therefore, f of x is continuous at x equal to c. We have shown that if f of x is differentiable at a point, then it is continuous at that point. Now the obvious question is whether the converse is true. That is, if a function is continuous at a point, whether it is differentiable at that point. In fact, the converse need not be true. If f of x is continuous at x equal to c, then f of x need not be differentiable at x equal to c. Consider an example f of x equal to mod x at x equal to 0. First, let us find out the left hand limit. Left hand limit is limit of f of x as x tends to 0 minus, which is equal to 0. The right hand limit is limit of f of x as x tends to 0 plus, this is again equal to 0. The value of this function at 0 is equal to mod 0, which is again equal to 0. Since LHL equal to RHL equal to f of 0, clearly the function is continuous at x equal to 0. Now let us check whether it is differentiable at x equal to 0 or not. First, let me consider the left hand derivative. The left hand derivative L of f dash of 0 is equal to limit of f of x minus f of 0 divided by x minus 0 as x tends to 0 minus. To find out this, I substitute x equal to 0 minus h and take limit as h tends to 0. I get limit of h by minus h, which is equal to minus 1. Similarly, if I find out the right hand derivative r of f dash of 0, this will be equal to limit of h by h, which is equal to 1. Since left hand derivative is not equal to right hand derivative, f of x is not differentiable at x equal to 0. Though the function f of x equal to mod x is continuous at x equal to 0, it is not differentiable at x equal to 0. Therefore, if a function is continuous at x equal to c, then it need not be differentiable at x equal to c.